In this video, we'll continue our discussion of sampling distributions, this time focusing on sample means. Let's talk about Shakespeare. Love him or hate him, you have to admit he certainly made an impression on history. Not only did his numerous plays become entrenched in our culture, but even the individual words he used had a lasting impact on the English language. Lots of words you use every day were actually first coined by Shakespeare. Words like majestic, laughable, monumental, amazement, bump, road, and elbow. Yes, seriously, elbow was a word invented by Shakespeare. Makes you wonder, what did they used to call it before then? Who knows? Anyway, let's fast forward to the modern age, when we can take a look at old works with a new lens. Thanks to websites like Kaggle and a little bit of coding in Python, we can take a big data look at all of the words in Shakespeare's plays, over 800,000 of them total, and generate data about how many letters long each word is. And speaking of words, what words could we use to describe this distribution of data? Well, it's unimodal, but it's certainly not symmetric. It's heavily skewed right. Most words are pretty short, but then you get some really long ones. There's even a 27-letter word in there, honorificabilitudinitatis. Say that one 3 times fast. All in all, the mean word length is about 4.078 letters, and the standard deviation is about 1.987 letters. Okay, let's see what happens if we take a random sample of words from Shakespeare. Here I've got a simple random sample of 30 words. Just like we'd expect, most words are short, but a few are decently long. Notice that some words appear more than once, like is and all. That should be no surprise, because those short words are the ones we use the most often in everyday language. The mean word length from our sample, X bar, is about 4.166 letters. Decently close to our population mean we saw earlier. But a different sample of words might lead to a different value for X bar. So I went ahead and did this 100 times, picking 100 simple random samples of 30 words each from Shakespeare's plays, and averaging the lengths of each word. Here's the histogram I got, though keep in mind yours could be a little different if you did this yourself. Notice that we got one sample with an unusually high average length, but that's the kind of thing that can happen when things are random. It's improbable, but not impossible. Now wait a minute. If you squint just a little, would you look at that? There's that normal distribution shape again. Once again, this is no coincidence. That happens pretty often with the sampling distribution of the sample mean, that is, X bar. If our sample size is large enough, that is at least 30, then the central limit theorem tells us that X bar will be approximately normally distributed, as we've just seen here. And that's true regardless of the fact that our original distribution was heavily skewed to the right. That didn't keep the sample means from being normally distributed, so that's really convenient for us. But it gets better. If you're lucky enough that the thing you're measuring from the population is normally distributed itself, then your sample means will be exactly normally distributed, regardless of your sample size, no matter how big or small. In either case, the mean of our sampling distribution matches the mean of our population. And the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. So, in our case from earlier with Shakespeare's plays, we would expect our sample means to be pretty close to 4.078 letters long. And the standard error, assuming a sample size of 30, should be our population standard deviation of 1.987 letters divided by the square root of 30. That comes out to about 0.363. And if we look at all the sample means we actually got, we can see that our actual mean and standard deviation came out pretty close to what we'd expect, so everything checks out. So to wrap things up, here's a summary of everything we've talked about with sampling distributions. take a bit to compare how we do things for proportions and how we do things for means. There are a lot of similarities. And finding those similarities is a great way to make sure you understand how everything fits together.